Well, I think I'm going to take the opportunity to begin. We're going to start a few minutes early. We have a significant number of people who have already joined the webinar, and I want to thank everyone for deciding to set aside 1 hour of your time today. This is certainly a different environment than we imagined when we invited everyone to this webinar a couple of months ago. I know a number of you are perhaps working from home, as most of us who are hosting this webinar are doing. But we press on and do the best we can. In the next hour, we're going to cover how to solve 4 common conveyor problems. Today, I'm the main presenter for Romeka Corporation, Mike Gawinski, and I'm happy to say that I'm joined by 3 colleagues. Brian Vraplik, our Director of Sales and Marketing, Jay Graham, Director of Operations, and Steve Forbes, our Product Engineer, all of whom can listen in and interject comments as needs be. These gentlemen are also able and willing to collect your questions or your comments as you type them. Feel free to use your chat dialog box at any time during the presentation to send questions along. We plan to leave some time at the end of this conference for a discussion. Romeka Corporation is hosting this conference. We have a facility in Wilmington, North Carolina. As of today, we are still making motorized pulleys and repairing motorized pulleys. We are classified as essential in light of the COVID-19 response to the virus because we supply products to food processors. We have 11 folks at the moment, 4 of them at their facility. The rest of us are in our homes. We're part of the International Romeka Group. For those of you that don't know, we are scattered around the world with facilities and sales offices in more than 24 countries. We're headquartered in Bergamo, Italy, which unfortunately has suffered greatly these last few weeks with the virus. However, our people are essential administrative people are working from home as we are. And we have about 1,200 people worldwide working to produce rollers, motorized pulleys, and components for the global materials handling market. We were founded in 1962. Group turnover is about $200 million, and we're a privately owned group. I'm happy to welcome everyone to our conference today, and I know we have end users, we have engineers, we have manufacturers, we have Romeka distributors, Romeka sales representatives, and we even have some Romeka affiliates joining us from around the world. Thank you for coming. Before we begin our formal webinar, I want to announce that we've made a decision to change the sales school that we planned to hold in our facility on May 7th and 8th to be a webinar. So you'll be contacted about that separately. Our distributor and our sales representative, people who are thinking about coming, we won't be hosting it in light of the virus, but we'll rather conduct a 1.5-day webinar to meet the needs of our sales folks. Let's talk about where we're going in the next hour. Webinar number 103 is intended to identify and help you avoid 4 common belt conveyor problems, namely drive motor burnout, excess hopper feeder pressure, excess skirtboard drag, and excess belt cleaner drag. And as you can see listed here, we've produced a variety of videos already addressing those topics. Some of you may have already seen those videos. Some are rather short, some are quite long and comprehensive. And I want to say at the outset that we don't much care about what you know, but we absolutely care about what you understand. And so our time together in the next hour will be our attempt to help you understand these concepts as best we can do. If you were to go to the Romeka Corporation YouTube channel, you would see this as the webinar playlist. We've had 2 webinars, one last year in March and another one last year in July. These have been recorded and are there for your use. You can also, of course, send a link to any colleague whom you think would benefit from looking at those webinars. Another playlist on the YouTube channel and also on our website are these how-to tutorials. As you can see, we've produced a bunch of videos. The one on the upper left-hand corner is our most popular one with nearly 20,000 views since we posted it a year ago. The second most popular one is directly beneath it, and they address how to calculate belt pull or how to calculate belt pull in bulk handling applications. Going down the left-hand column, the two videos on hopper feeder drive technology are also very popular with thousands of views each. And we would encourage all of you participants to avail yourselves of that video resource. We will continue to add to this. And in fact, today's webinar consists of excerpts from those videos. Let's address the topic at hand. Why do conveyor problems occur? They could occur because wrong equipment was installed, and that's not what we're covering in this webinar. Or they could occur because correct equipment was installed, but something changed. Maybe the handling rate changed. The process needed to go from 400 tons per hour to 800 tons per hour. Perhaps the type of material changed. You've had to stop handling wood chips and now you handle iron ore. You were handling stone and now you're handling sand. Maybe the ambient conditions changed. Temperatures are lower than was anticipated. Or maybe the equipment was made for one environment, but it was sold and redeployed in a colder area. Maybe the current conveyor parameters changed. The length needed to be increased, or belt cleaners needed to be added because the material was stickier than was originally anticipated. Perhaps the belt speed was increased, or the skirtboard system was modified, so forth. What is the actual failure mode that you're addressing? Is your motor tripping out and causing a nuisance and causing delays to your production, or is the motor actually burning out, which of course would be a minor disaster because as the motor burns out, it would take longer to get the conveyor up again? Or is some other conveyor drive mechanical failure the failure mode that you're addressing? We'll be talking about common causes of motor burnout. We'll be addressing how to avoid electrical causes in the first fourth of this presentation, the first segment of this presentation, motor burnout. We'll talk about how to avoid electrical causes. We'll talk about how to avoid mechanical causes. And in fact, the largest part of what we'll be discussing today is avoiding mechanical causes. And then we'll talk about how to protect motors. We'll be addressing hopper pressure relief in the second segment. We'll define drag. We'll look at some pertinent equations, defining active zone, parabolic volume versus a prism, talk about cutting factor and so forth. We'll demonstrate briefly the software which we have downloadable for your use, and we'll explain and describe pressure relief, what it is and how to do it. In the skirtboard segment, we'll be defining skirtboard system drag. I'll present some pertinent equations from the Conveyor Equipment Manufacturers Association manual and give you some suggestions as to how we think you can simplify those calculation techniques. Another demonstration on software, and then some ideas on how to relieve excess skirtboard drag. And then finally, the fourth segment, short segment, will be on addressing belt cleaner drag. We'll define it, we'll talk about the equations, I'll demonstrate the software, and we'll look at some techniques on how to minimize belt cleaner drag. Now let's address the first fourth of this hour together, a large fourth, drive motor burnout. What are the common causes of motor burnout? Well, wrong voltage is a cause, unbalanced phases is a cause, and too much current is a cause of motor burnout. And overwhelmingly, too much current is the largest reason we see motors coming back to us from burnout. And normally, the excess current is from overload as opposed to some electrical problem. Let's address electrical causes initially. Supply voltage could be wrong. You should use a multimeter to verify your power supply voltage that the motor is correct. Another problem is a voltage surge. Now, if you're driving your motor, any kind of a motor with a VFD, it's essential that you filter the output if you're going to install your VFD more than 30 feet from the motor, because the VFD can cause what is called a resonance-induced voltage surge. In fact, if you look at the photo on the right, a voltage surge has a distinctive look. You can see a localized burn or a pinprick in the stator head. You can also check for a lightning strike. It'll resemble what you see on the right as far as a localized dramatic burn. Imbalanced phases can also occur. You should make sure that the current draw in each motor phase, measure the current draw in each motor phase, and verify that the power company supply is balanced. We'll show you how to do that in a minute. And you should also check for incorrect single-phase draw-off of the three-phase power supply in the plant. The first balance problem would be from the power company. The second balance problem would be inside the plant, and both should be checked. Now, here are two excerpts from our troubleshooting video, and here's how you could use a multimeter to check your situation. You should use your voltmeter to measure the supply voltage between U and V, V and W, W and U. Check the voltage across those terminals, and the voltage should be balanced and should not have more than 5% deviation from the lowest to the highest. And the three voltage measurements should be within 5% of the voltage rating on the data plate. That's going to verify that the supply voltage is getting to the pulley terminal board and is the correct amount and is balanced. The circuit diagram that you see on the lower right-hand corner is taken from a Romeca motorized pulley terminal box. You can see indicated in the middle of the circle the three brass pegs, U, V, and W. And you can see that they're connected to the power supply, phase 1 to U, phase 2 to V, and phase 3 to W. Also, you'll see indicated at the bottom of that large circle, pegs labeled T1 and T2. This is where we bring out our thermal protection switches, but more about that later. You should also use your multimeter when troubleshooting your motor to measure the current. Use the clamp-on feature and check the current draw at the wire that leads to peg U, check it in the wire that leads to peg V, and the wire that leads to peg W. Those three measurements should be balanced and not have more than 10% deviation from the lowest to the highest. And they absolutely should be less than the FLA, the full load amp rating shown on the data plate of the motor. That's going to help you verify that the motor windings are balanced. And it's also going to help you verify that the motor is drawing the correct amount of amperage. We have a lot to say about what is the correct amount of amperage. This is how a motor looks when it's been stressed, when it's been burned out normally from too much current flowing in the stator, which is a cause of too much torque applied to the motor. We're going to talk in the next few minutes about avoiding mechanical causes. You should check required power. You should calculate and compare your required power with your installed power. I'll show you how to do that in a minute. You should also check for physical extra drag. Inspect your conveyor. Is something new occurring that has caused this? And we'll conclude the first fourth of the webinar by looking at ways to protect motors, verify your overcurrent settings, install thermal protection, and then if needs be, install a more powerful motor, if that in fact is the solution you need. It's important to define some terms at this point if we're talking about overloading a motor, a conveyor drive motor. Every conveyor needs a certain amount of pull to pull the product uphill. In the case of this inclined conveyor, we define the term TE as effective tension. And in imperial units, we think of TE in terms of pounds of force. Every conveyor needs a certain amount of effective tension to do its job. Now, going through this equation in depth is beyond the scope of this webinar. However, this is what's known as the SEMA design guide historical method for calculating effective tension. You can see you can break it down into three parts. How much tension do we need to apply to the belt to overcome friction? how much tension do we need to apply to the belt to overcome gravity, and how much tension do we need to apply to overcome momentum. Those terms have all been built into a piece of software which is downloadable from the Romeca Corporation website, and we use it on a daily basis. So to simplify the idea of required conveyor power, think of it like this. You need to figure out how many pounds you need to pull on the conveyor, and you need to decide on the belt speed. Once you have selected those two things, you know the amount of required power, because required power is nothing more than the product of the two terms. In other words, TE in pounds times V in feet per minute is a certain number of foot-pounds per minute. And since we know that 1 horsepower equals 33,000 foot-pounds per minute, once we multiply belt tension and belt speed, and we come out with a certain number of foot-pounds per minute, we divide by 33,000, and we have our answer in horsepower. And you can see here a comparison between imperial units on the top and metric units on the bottom. So as an example, let's say we need to pull on the belt with a force of 1,000 pounds. And let's say we're going to run the conveyor at 330 feet per minute. Well, we know we have 330,000 foot-pounds per minute. Divide that by 33,000, we know that we need 10 horsepower to do the job. In metric units, let's assume that we're going to need 4,400 newtons to pull on the conveyor, and we've decided on a belt speed of 1.7 meters per second. Well, we know that our power requirement is 7,480 Newton meters per second. Divide by 1,000, and our answer comes out as 7.48 kilowatts. And just for your information, the amount of power required in both of these instances is identical. In other words, 10 horsepower equals 7.5 kilowatt. Now let's have a look at where this motor burning problem could occur and why it would occur. We're using as an example a Romeca motorized pulley as the conveyor drive, and I'm highlighted for you here the stator and the rotor. Well, as current flows through the stator wires, magnetic flux causes the rotor to spin, and it's the spinning rotor that does the job for us, because the rotor spins, it turns the gears engage the pulley shell. So the moving components are rotor and shell. Notice that an AC squirrel cage induction motor has no built-in ability to limit its current flow. That is extremely important for you to understand. There's no built-in ability to limit the amount of current flow. Therefore, if the motor is subjected to a load which is higher than its design load, it will burn itself up by drawing more current than it's designed for. And for your information, most motor burnouts occur in the stator windings as opposed to wire leads or something like that. You'll see the evidence of an overload in the stator itself. Now we'll look at the same thing in a different way. This is a cross-section of a Romeca motorized pulley with the stator highlighted. You can see that we have the stator, we have the rotor, we have the gearbox, and the shell. In steady state, we are throwing heat away continuously from the hot stator through the pulley shell and into the conveyor belt. We use a conveyor belt as an infinite heat sink. As a matter of fact, we use oil as a heat transfer medium. This oil that circulates, it circulates by means of drip lips, which we weld to the inner surface of the pulley shell. They act like a water wheel, pulling oil from down below and dropping it on the hot stator, pulling the heat from the stator, depositing it back into the oil, which spreads the heat across the face of the pulley and throws the heat more or less evenly into the conveyor belt to keep the stator cool. In the case of a TEFC motor, the idea is the same. A fan is installed on the rotor shaft externally, and the fan draws ambient air across the cooling fins to dissipate the internal heat. And if overloaded, these drives will fail in the same mode as an internally powered conveyor would. In other words, the stator will burn. because either the copper wire gauge or the wire insulation or the stator paper or the lacquer are not designed to handle the extra amperage and therefore the higher motor heat. Now, I would like to point out for you the relationship, the important relationship between horsepower and current draw. Or we could think of it in a different way, design power in horsepower and FLA, full load amps. Before you see 8 different conveyor drives, from a lower power drive on the left to a higher power drive on the right. The 4 examples on the left are from our Model 400 motorized pulley. The 4 examples on the right are from the larger Model 500. The higher the power, the higher the FLA. So let's have a look at a 20 horsepower motorized pulley. The current draw for 20 horsepower is 23.6 amps. FLA is 23.6. In the case of a 15 horsepower motorized pulley, the current draw is less than 20 amps. And in the case of the Model 500, the 25 horsepower drive has a full load amp draw of more than 30 amps. Now, have a look at an actual case that we recorded nearly 20 years ago. This is an actual case in which motors were periodically burning up. They were 20 horsepower motors. You can see with the purple line in front of you, the horizontal purple line, that is FLA at 23.6. I draw your attention to what happened on Thursday, April 29th, 2002. The amount of current drawn through the motor exceeded FLA numerous times. In one case, it was almost 35 amps. And so I have to ask the question, this 24-hour period was typical of what we measured throughout the week. Why was the motor overloaded? And why was the motor allowed to carry more amps than FLA? Answer, the wrong motor was installed and the overcurrent setting was adjusted. Simple as that. In this case, a 20 horsepower motor was installed and a 25 horsepower motor was needed. And the reason the motors were burning up is because the overcurrent setting was adjusted to some number above FLA, which of course is a no-no. This is not the actual motor, but it's a similar motor, and the damage was uniformly burned. We could see from the evidence that it was uniformly burned and overstressed. I draw to your attention the photo on the right. You're looking at a contactor with an adjustable overcurrent protection. Hopefully you'll be able to read it there. You can see that you could set the overcurrent on this switch to 4 amps, 5 amps, or 6 amps. Why would a device like this would be used? Well, it's simple, because if you have 20 or 30 or 40 conveyors and all of them would be drawing, say, something like 4 amps or 5 amps or 6 amps, you could buy one switch and set it up to control the appropriate drive. The motors that had a full load amp rating of 4 would have a starter set at 4. Those that would have an FLA at 5 would have the overcurrent setting set at 5. The problem is, if the motors that were set with an FLA setting of 4, let's say they were set at 4, if those motors tripped out and caused nuisance trips, there's a temptation to take a screwdriver and simply adjust the overcurrent setting. And that in fact was done in the case I mentioned previously. If in fact you increase the overcurrent setting, you are eliminating any overcurrent protection. So now the motor is running without protection, which of course can be a disaster for the motor because it has no internal means of protecting itself. What I'm showing for you here is how Romeca motorized pulleys are protected with an extra, we call it extra layer of protection. We build our motorized pulleys with 3 bimetallic thermal protection switches in each stator. You can see on the diagram on the upper right, the 3 bimetallic switches are wired in series. These are actually in the stator head and brought out to a common pair labeled T1 and T2, as I mentioned previously. On the lower right, you can see the circuit diagram I alluded to before. T1 and T2 are the brass pegs where the operator would attach the internal thermal protection switches to a normally closed control circuit. That's indicated at the circuit diagram on the lower right. In this case, we show an example where they're connected to a 115 volt single phase 60 hertz normally closed circuit. This would give the operator two levels of protection. One, the initial level of defense would be overcurrent protection in the starter, and the second level of protection would be thermal protection. Here you can see a circuit diagram, a simplified circuit diagram of a typical conveyor belt. As you go from left to right, you'll see a variety of switches. The switch on the left could be an on-off switch. That could be in the operator's cab, or it could be on the manual on-off switch on the handrail by the catwalk by the conveyor. Going from left to right, you might have a belt misalignment switch. The one in the center indicates a switch for emergency pull cord, which is typical. On the right was another belt misalignment switch and a plug suit switch. These are all typical switches that might be installed on a normally closed control circuit for a conveyor. Now I draw your attention to the protection. Here you see indicated overcurrent protection, and this is intended to show that the starter has a built-in overcurrent switch set at an appropriate level. These starters can come with fixed overcurrent settings, or they can come with adjustable, as I showed previously. Of course, if you install one with a fixed overcurrent setting, which is not adjustable, then the designer and the builder of the system is assured that there'll be no temptation for operations people to adjust them later on. The second thing I want to draw to your attention is the symbol for thermal protection. So on this circuit diagram, this motor is protected in two ways. One with overcurrent protection in the starter, and also with the built-in thermal protection in the motor. And of course, the switches are connected to a normally closed control circuit. That concludes the motor portion of our talk. And now I would like to turn our attention to excess hopper feeder pressure. What do we do about that? Let's define hopper feeder drag. Let's look at some pertinent equations and some pertinent terms, and let's have a little demonstration of the Romeca Corporation software, and let's conclude with the concept of pressure relief, what to do and where to do it. Hoppers can be used for a variety of reasons. The hoppers on the left are simple storage hoppers. The hoppers on the right are used for blending. In these slides, the two slides on the left show that hoppers can be used to serve as an interface between batch unloading and continuous takeaway. For example, on the upper left, batch unloading with a clamshell of a barge feeding through a hopper into a continuously flowing dock conveyor. And lastly, the hopper on the right indicates hoppers used as a metering device. In this case, these hopper feeders have their speeds either increased or decreased so as to provide a certain design rate into the gyratory crushers beneath them. Let's look at some terms now. Special hopper load on feeder conveyor. We know that the special load consists of a vertical load which comes from the hopper onto the top of the conveyor belt. And that needs to be, and it will provide a force like a snow plow plowing snow on the street. That force is felt in the conveyor belt, and the drive needs to be large enough to overcome that drag. Well, before you see an empty hopper and a full hopper. So the question is, what force in the belt do we need to apply to overcome the hopper load? Do we need to consider the entire weight of the material in the hopper or not? And the answer is not. We do not need to consider the weight of all the material in the hopper, but rather the material contained in what we call the active volume. the active volume. And the active volume can be thought of as having a parabolic shape. All the other material can be thought of as self-supporting and irrelevant to the amount of drag the conveyor drive needs to apply to the feeder conveyor. So the question is, how do we calculate that force? It's not as difficult as you would think. We need to calculate the volume in the active zone. We need to calculate the weight of that material, and we need to apply a factor in order to determine the cutting force. And it's no more complicated than this. We consider the parabolic shape to be a prism. We consider the parabolic shape in the active volume to be a prism. We multiply hopper opening width by hopper opening length, and then we multiply that area by the height. We set the height equal to 3 times the width or 3 times the length, whichever is smaller. I'll say it again. We multiply the hopper opening width by the hopper opening length, and then we multiply that area by the height, which equals either 3 times the width or 3 times the length, whichever is smaller. That gives us a volume. We would know the bulk density of our material in pounds per cubic foot, for example. That gives us the total weight in the active volume, and we simply multiply that by a cutting force, by a factor of 0.5 to get the cutting force. So the magic number here is 0.5. The cutting force equals 1/2 of the weight of the material in the active volume. We need to add that force, of course, to the overall conveyor force in the belt to move the material. Now we turn our attention to pressure relief. What is it and why is it? Since the cutting force is equal to the volume of the active zone, if we can decrease the volume of the active zone without impeding the material flow, we can decrease the required cutting force. On the left, you see an actual case from a shipping facility in Virginia. You can see that an inverted tent has been welded to the hopper opening, changing one opening into 2 openings. And the calculation of the cutting force is identical to what I showed previously, except you simply take the width times the length times the height of each of the 2 smaller hopper openings. Calculate the volume, calculate the weight, multiply by 0.5, and you have the hopper force that's needed, as you can see here. And in 4 openings, obviously you'll simply have 4 small prisms. Calculate the volume of 4 small prisms, calculate their weight, multiply by 0.5, and you have the needed cutting force. This summarizes an example, which is an excerpt from the video we produced. You can see, as shown here, we have, as an example, a conveyor which required 1 horsepower to run with no hopper load. With 1 opening, it had an active volume of 154 cubic feet, and with 4 openings, it has an active volume of 77 cubic feet. That, of course, decreases the drag load dramatically from nearly 6,800 pounds to 3,400 pounds, and decreases the horsepower from 20.5 to 10.3. So when we add in drivetrain losses, as you can see on the chart, we come up with 2 different amounts of power to do essentially the same job. 1 opening requires 23.2 horsepower, 4 openings, hopefully without any flow restrictions whatsoever, has a belt drive power requirement of 12.2. This is an example for you of wrong hopper pressure relief. If you look on the left, you're looking at the view from up above. You can see that an inverted angle was welded across the hopper opening, and then 10 small angles were welded to that large angle, giving 1, 2, 3, 4, 5, 6, 12 openings, taking 1 large opening creating it to 12 small openings. The problem was the pressure relief was installed too high. It was installed so high above the opening that an enormous amount of material was allowed to flow through the openings and press down on the conveyor at the actual hopper opening. This slide shows Rumeka's recommendation to the customer, and this is a variety of ways that we said the hopper opening could be converted from one large opening to several smaller openings. That actually was put in place and was effective. Now I would like to turn our attention. By the way, let me stop. This is 10:30. I want to ask either Brian or Steve, have any questions come in that we need to talk about? If not, I'm going to keep on schedule, but I would like to just find out if any questions have come in at this point.
No, I think we're good.
Okay, great. Then I'm going to keep pressing on. We have before us 2 more segments to cover. One is on skirtboard system drag, and the last one would be belt cleaner drag. So let's go through some definitions of skirtboard system drag. We'll look at some pertinent equations for board drag and seal drag, and have a little demonstration fairly quickly of our downloadable software. And then we'll talk about what to do about excess drag, how to relieve it. First, we define a skirtboard system. A skirtboard system consists of a board, which essentially contains material as it stabilizes within a trough. Typically, a skirtboard is going to be in the range of 12 to 15 feet long. And the other important component of a skirtboard system is its seal. The seal can either be, as you see illustrated from left to right, a vertical seal, a perpendicular seal, or an oblique seal. We've not shown the so-called parallel seal or contactless seal, but in any event, a skirtboard system will have some sort of a seal. The purpose, of course, is to contain and capture fugitive dust within the skirtboard system as the material stabilizes. Here you have what is called the SEMA historical equation for calculating skirtboard system drag. One component shows board drag, the other component shows seal drag. On the left in the illustration, we show the dimension LB, the length of the skirt zone, LB in feet. In the middle, you can see the cross section of material as it is stabilizing. And on the right, you see the detail, which highlights dimension HS. This is the height of material as it rubs against the board. Of course, it's important to minimize HS because the amount of drag on the board is a significant component to the overall skirtboard system drag. Let's look at this in more detail. T equals CS times LB times HS squared plus 6LB. Let's break it down. CS is material coefficient of friction. And on the right in the table, you can see a very small excerpt from a very large chart of material coefficients provided by SEMA and the design manual. You can see that iron ore has a frictional coefficient of 0.276. Whereas wood chips has a very small frictional coefficient of 0.01. This is a very small excerpt from our 10-minute set of videos on this subject. These material frictional coefficients are available in the SEMA guideline. The length of the skirt zone and the height of the material which rubs against the board are defined. As we look at seal drag, the defined on the lower left-hand corner of the slide, that equals 3 pounds per foot of seal times the number of seals, which is usually 2, times the length of the skirt zone. Now an example. If we think of iron ore, in this case, which is one of the highest frictional coefficients that we know of, we have the number 0.276. If we multiply 0.276 times the length, which is 15 feet, times 4 inches squared, which equals 16, we come up with a board drag component of 66 pounds, and we look at seal drag, which equals 3 pounds per foot per seal times 2 seals times 15 feet. We see that we have 90 pounds for a total of 156 pounds of skirtboard system drag in this 15-foot skirtboard area. How do we take that drag and convert it into a useful unit of measure? Well, all we need is the belt speed to multiply against the drag, and then we find the amount of power that's required. So on the right, you can see that our example will have a belt speed of 15 feet per minute. 156 times 600 is 93,600 foot-pounds per minute, which of course, as you see, equals 2.8 horsepower. We divide by 33,000 to come up with the answer of 2.8 horsepower. Now, if our conveyor is 10 horsepower, this amount of drag is significant. It's 28%. If, on the other hand, our conveyor is long or heavily loaded and the required power, total required power is 300, then the amount of skirtboard system drag would be quite small. Here is one way in which a user can use our downloadable software. And before you see an example. This is an excerpt from the video. On the left, we have an operator who is handling 575 tons per hour of material with a belt speed of 300 feet per minute. The essence that I want to point out to you is that the material is filled to what SEMA recommends as the maximum. In other words, the fill factor is 100%, and that's indicated by the yellow arrow on the left. So at 575 tons per hour, 300 feet per minute on this belt width, we have the conveyor completely full, and 8.3 horsepower is required. Let's say the designer would select a 10 horsepower drive, which seems reasonable under these circumstances. Now, if you turn your attention to the diagram on the right, you can see what would happen if the operator is challenged to move 800 tons per hour on the same conveyor system at 300 feet per minute. You see that the cross-section exceeds SEMA's recommended fill factor. As a matter of fact, it shows that it's 138% of what SEMA recommends be carried on this conveyor at this belt speed. Notice that the required amount of power is 9.9 horsepower. There would be a temptation to just press on because we have enough power installed, but that's would be asking for trouble because with it this full, especially in the loading area, there would be a tremendous amount of spillage, and it's not recommended. So therefore, something would need to be done. And as we mentioned in our longer video, if one were to install skirt boards through the entire length, the conveyor, by the way, is 150 feet long. If one were to install skirt boards, you would contain the material and you would limit spillage. However, the amount of horsepower that would be required would be 18.7. If you look at the diagram on the right, you can see a more sensible way of solving the problem of the higher tonnage rate would be to speed the conveyor up. You can see that we are handling 800 tons per hour at 415 feet per minute instead of 300 feet per minute. And we are back at the SEMA recommended 100% fill factor, which means that theoretically there will be no spillage. And the power requirement is 12.1 horsepower. Notice on the left, the solution is 18.7 horsepower. So the solution on the right is 12.1 horsepower. We would recommend the solution on the right because the kilowatt hours in this example would be far less. Maybe a 15 horsepower could be installed to do the job more efficiently than the one on the left. And I also should say that a skirt board, the full length, would be problematic in the sense that it would require constant maintenance of seal system, 150 feet of seal system instead of 12 feet of seal system. Now I would like to draw our attention to the fourth and final segment of this webinar, which is what to do about excess belt cleaner drag. We'll define it, we'll look at some equations, we'll look at some software examples, and we'll talk about what to do about it. Well, a belt cleaner, as I'm sure practically everyone would know, is defined as one or more mechanical devices pressed against the surface of the conveyor belt on the dirty side to stop carryback or prevent carryback. If carryback is allowed to continue, it will build up beneath return idlers, and it has the potential of damaging return idlers and even damaging belt. The pressure of a belt cleaner against the belt is usually provided by a system of counterweight or springs or some sort of a torsion device. Other low friction devices such as brushes and wash boxes may be used, but they're not covered in this webinar. We're talking about devices which press against the surface of the belt. So here are some examples. You can see on the left a primary cleaner, meaning a first cleaner, located at the horizontal center line of the pulley. In this example, it consists of a thick UHMW blade. The center example shows a primary cleaner, meaning the first cleaner or the only cleaner, is located near the vertical center line of the pulley, slightly behind the vertical center line, and it consists of thin tungsten carbide blades. The illustration on the right shows a secondary cleaner, meaning a second cleaner, not the primary cleaner. It's not necessary to have a secondary cleaner all the time, but sometimes it's necessary. So here's an example of one. This one is behind the vertical center line of the pulley, maybe 2 feet or something like that, 1 feet or 2 feet behind the vertical center line. And it consists of a series of thin tungsten carbide blades. Let's look at some equations now. SEMA recommends that to calculate belt cleaner drag, SEMA says that belt cleaner drag could be anywhere from 2 to 14 pounds per inch of scraper blade contact, depending upon the type of belt cleaner that's used. And Romeca has used for years and years SEMA's recommendation of using 5 pounds per inch of width when the type of blade is not known. And we would recommend, Romeca would recommend, that we conservatively estimate belt cleaner drag by using 5 pounds per inch of belt width rather than 5 pounds per inch of cleaner contact. You can see that illustrated on the right. Let's say that in our example, the red indicates a primary cleaner and a secondary cleaner, and the red cleaner is 24 inches wide on a 30-inch wide belt. To be conservative, we would say for belt cleaner drag, a conservative estimate, use 5 pounds per inch of belt width times 30 inches, in this example, times 2, since we have a primary and a secondary. And we would come up with a belt drag figure of 300 pounds. Converting that to a useful unit of measure, we simply multiply the drag, as we did in the other two examples, by the belt speed. In this example, if our belt speed is 300 feet per minute, 300 times 300 would yield a power requirement of 90,000 foot-pounds per minute, which converts to 2.7 horsepower. As I said before, in the skirtboard example, I'll say again, if this conveyor is driven with a system of 10 horsepower, conveyor drive system of 10 horsepower, and you add a couple of belt cleaners that require 2.7 horsepower, you've just added 27% to the required power for that conveyor drive to supply, which is quite a bit. And so it's a good idea to be aware of what belt cleaner drag can do to the required power of a conveyor drive system. Here are some excerpts from the software that we've made available and we use on a regular basis. You see 3 screen captures of the output. On the left, you'll see that we have a 100-foot long conveyor handling 500 tons per hour with a belt speed of 300 feet per minute, and there is no belt cleaner installed. So the program tells us the amount of power required is 5.3 horsepower. On the upper right, you see an excerpt from our program which shows that 1 belt cleaner has been installed, and our power requirement jumps to 6.7 horsepower. On the lower right, you can see the excerpt that shows that 2 cleaners have been added and our total power requirement is now 8.2 horsepower. Notice the problems that could occur if in fact the designer realized he needs 5.3 horsepower and decided to install a 7.5 horsepower drive and then added 2 belt cleaners. He's got a little bit of trouble in that case. The point is that this program can show you the required power with a click of a key, and this can be done after a conveyor is installed. If things have changed, you can put the parameters into the program and find out where the problem lies. Now I show this example not because it's a belt cleaner example, but because it's an example of where drive power needed to be added to a conveyor. The case on the right is a radial stacker that was 30 years old at the time, and it had a 100 horsepower drive system installed at the tail. Their problem was belt slippage. In this case, when it rained, this material was like a detergent and got very slippery. So it was necessary to add an extra 180 degrees of belt wrap to the conveyor. And the solution to the problem was installing a motorized pulley at the head. Installing the motorized pulley at the head gave this operator 360 degrees of belt wrap, stopped the conveyor slippage problem cold. Why do I bring it up? I bring it up to say that if someone was to realize that he needed, because the material was sticky and there was nothing he could do about it, he needed more belt cleaners than was ever dreamed, and there was no getting around that problem, it's relatively straightforward to add extra power to a conveyor in a simple way by installing a motorized pulley somewhere on the conveyor. The illustration before you actually has the motorized pulley installed in a mechanical take-up. It's not a big deal to bolt down a driven, a type of motorized pulley drive in a mechanical take-up, because 2 bolts per side and you're done. As long as you festoon your power cord, you're good. So as we think about what can be done in the situation of excess belt cleaner drag, one question is, can the spring tension be relieved or the counterweight reduced? Sometimes that's not the case. Another idea is too much belt cleaner in contact with the belt. In other words, the dirty area is always almost always the center of the belt. If on a 30-inch belt, the dirty area is 12 inches and you have 24 inches of belt cleaner, it might be a good idea to take off some of the blades and just have the blades be on the dirty section themselves. That would limit the drag. Is it possible to remove a cleaner? Have too many cleaners been put on? Can one be removed and still, can you still limit the amount of carryback? And as I said before, if none of those things is available to the operator and more power is needed, then perhaps the drive system could be replaced or an extra drive could be added to the conveyor. Well, that brings us to the end of our presentation. We've talked about 4 different things: drive motor burnout for conveyors, excess hopper feeder pressure, excess skirtboard drag, and excess belt cleaner drag. I want to thank everybody for listening to this presentation, and I would invite Brian and Steve and Jay to interject anything at this point.
Mike, this is Brian. I think it went well. I think questions were good, and certainly if anybody has any other questions, we'll hang out here for a little bit longer, and you can always send any additional questions to sales-us@rulmeca.com, and we'll be on the lookout for them. Thanks, everybody.
And I can also add to what Brian just said by letting you know that you will automatically receive an email from us thanking you for attending and soliciting any feedback. If you have any recommendations for us on what you'd like to see covered in a future seminar, please let us know. These are some things that we kicked around yesterday, just anticipating this question. Some of the things that we're thinking about, and I don't want to be negative, but I have to be realistic and say many people are working from home. It's going to be difficult for people to have customer visits in the normal way, at least for the foreseeable next few weeks, or God forbid, months and months. But it's reasonable to assume that a number of people will be working from home. And so if you have a desire for more training like this in 1 hour segments, for example, please let us know and we'll be happy to put it together as a service to our customers. And one thing that we thought about could be very interesting to people would be something on food processing conveyor drive technology. Brian and Zach in particular have lots to say on that subject, what it is, how we do it, how it can help people, and so on. Other things that we thought about were more of an elaboration on dual drive technology. How do you solve belt slippage problems? Can you elaborate on, Mike, can you elaborate on what you just talked about, that facility in Wyoming? What about belt bounce problems eliminated by dual drive technology? What about belt speed versus belt width optimization? Can you show us in an hour how to use your software to plot cross sections and plot trajectories and so forth and so on? So those are some things that we throw out there as stuff we would be willing to put together for however small or large the crowd of people interested in it would be. So once you get those automatic emails, please respond and tell us with what you'd like to see us talk about. We would really appreciate it. And I can see that we had a large number of people, many dozens of people who showed up for today's presentation. And I want to thank you all for sticking with us through this 60 minutes. I hope that you found it useful. And in closing, I just want to say a recording of this webinar will be put on our YouTube channel just as quickly as I can get it uploaded, hopefully within a couple of hours. And you can review it again at your leisure, or you can send a link to a colleague if you think we've covered something that would be beneficial to them. Once again, thanks everybody for your presentation. I'm going to conclude if I don't hear anything else to the contrary. We good, Brian?
Yeah, I would say let's hang out for another minute or so. There's still some questions trickling in.
I'm glad I double checked. Okay. Okay. I can see, Brian, I'm going to take the liberty of addressing one that Rod Ganther brought up. He said that I mentioned that if a customer had the opportunity to remove a couple of blades because there was too many blades in contact with the belt surface compared to how dirty the area was, can our program accommodate that? The answer is yes. We can easily do that. And I will tell you offline, Rod, how we would do that. So that's one question. Rod Ganther, got it. Mike Alphen asks if the SEMA guidelines are available to anyone, and the answer is yes. The SEMA design guide to conveyors can be purchased. There's an online version and there's a hard copy version, and you could get that from SEMA. Just go to, I think it's SEMA.com or SEMA.org. Mike, I'll find out and I'll tell you offline how to get it. But the answer is yes, it's available. It's a very handy book. Right now we're up to edition 7 by SEMA, and I neglected to mention earlier, all of the equations you saw in this presentation were based on the 4th edition, which are called the historical methodology. There is a universal method which SEMA has adopted, which is a different methodology. And Romecca Holding in Italy has created some software, or I should say is creating, we are now beta testing that software using the SEMA universal method to be, if you want to say, more up to date. The stuff that was demonstrated today is from a program I wrote over 25 years ago that's worked very well, very nicely and reliably. The new software will be an update in the sense that we'll be using the SEMA universal methods. That's Mike Alfred. I'll tell you how to get the book, Mike, in a separate email. Conveyor Equipment Manufacturers Association, Conveyor Design Guide. Let's see. You need someone, Steve Terrell mentioned that you need to divide calculated horsepower by drive efficiency to get the actual required horsepower. Yes. And I went through the presentation very quickly, but our program does allow for efficiency. In other words, so when the program says you need so-and-so horsepower, it takes into account the inefficiency of a motorized pulley. So it says, if it says you need this, it makes the correct recommendation as opposed to the bare horsepower. I was oversimplifying just to help people understand the equations rather than the various factors that are required to ensure that the drive is correctly sized. We do that automatically. Let's see. Brian, did I miss any other question?
It looks like we've addressed everything.
All right.
And you know, just to kind of reiterate this, because we got this question a couple different times about, you know, we use this 5 pounds per inch drag number. That's per SEMA calculations, but certainly different types of materials have different coefficients of friction. Different manufacturers use different, you know, say their coefficient of friction is lower than anybody else, and we get that. And if you have a fully skirted conveyor and conveyor skirtboard drag is starting to become an issue, and you want to use a certain manufacturer who has a much lower coefficient of friction according to them, well, then we would recommend that you reach out to that manufacturer and get the actual coefficient of friction. And then we have ways that we can work that coefficient of friction into our program. It's a little bit manual. We have to kind of help with that. We can do that. We can help you with that if we know what the actual number is.
I see that Rick Doherty wrote that sometimes end users will inadvertently overtension a conveyor belt in an effort to solve conveyor tracking problems. In other words, if a conveyor belt is mistraining in one direction, they tighten one side of the mechanical take-up, and then it mistrains the wrong way. Then they tighten the other side, then they tighten the first side, then they tighten the second side. In other words, rather than relieving, it's tighten, inadvertently overstressing the product mechanically. And one of the first slides I mentioned was, is your problem a mechanical damage? We mostly talked about motor overloading, but it is possible to have mechanical damage, and the mechanical damage would manifest itself in a variety of different ways. But generally, the mechanical damage that we see is from overtensioning the belt. The belt should not be overtensioned in an attempt to track the belt, and the belt should absolutely not be overtensioned in an attempt to stop slippage. There's a better way of stopping slippage than tightening the belt to make it look like a piano wire. And if anybody has specific comments or questions about that, we invite all of that stuff, and we will respond to you via email one by one. I hope that addressed what you were thinking about, Rick. Okay, I think that pretty much answers all the questions. Yes. Well, it's 11 o'clock, at least by my watch, and so I'm going to conclude the webinar at this time. As I said before, I'll be sure to put the recording on our YouTube channel as well as our website. Thanks, everyone. Goodbye. We appreciate your attendance.